Good day, ladies and gents. Welcome to this worked class example where we're going to be looking at calculating loads on structures. This first specific video we're going to be looking at wind loading, and then the second one we're going to be looking then at live loads, dead loads, or permanent and imposed loads, and then load combinations, but it's all part of one large example. So here you'll see the question listed. I'm not going to read through everything, but just summarize a couple of things. If you need to read it, you can just pause this video if you don't have a copy of the PDF this is from. But we have a storage facility built at a chemical factory in South Africa, and this structure was actually built at a site, but just not according to these details. And we're going to calculate the structural loading. Firstly, the client has provided weights of pipe, services, and equipment at about 35 kilograms a square meter. We've got roof sheeting and insulation on the walls. Then the structure altitude is about 350 meters above mean sea level in eThekwini in Durban, and it's on an industrial area on the outskirts of town. And then terrain category is between B and C. We've got a roller shutter door and a pedestrian door, which will influence our internal pressures. We also have a load of 6 kilonewtons, a point load that could be applied from the apex of the frame in any bay. And then we've also given that there's about a 30 millimeter gap all the way around the edge that can influence leakages. And just as a note, in this course, if you're not given leakages, you can assume them to be negligible. They're very difficult to approximate in real life anyway. So the questions are: answer the following. To determine the peak wind pressure for the design of the building, and then following that, determine the external pressure coefficients for the roof and walls when the wind blows from grid line A to C and grid line 1 to 6. And then we've got to determine internal pressure coefficients for two cases: when doors are open and doors are closed. We're going to determine line loads to be applied, and then the last ones, those ones we will go 5 and 6 we will go on to in the next video, where we have to determine imposed and permanent loads, and then we're going to list the load combinations. Now here is a look at the structure. So this is a plan view. It's a typical portal frame structure. It's got 6 bays and 7 portal frames, 6 bays. Purlins, girts, and sizes of members are here, and then here is a typical cross section through the structure. So you can see it's I-beams portal framed, base connections to bases, girts around the side, purlins on top, some knee braces. But the main thing is we're going to be looking at the load placed on the sheeting. So the load that the wind is applying to all that sheeting. So the sheeting picks up the load, then the purlins and girts carry the sheeting, and then those loads are distributed to the portal frames. So we're going to now start going through those different questions and applying it to the structure. The main couple of things is just that we have a height of structure of about 4 meters off the ground, and then there's another about 1.5 meters from the eaves right up to the apex, and then the total width of the structure is 15.7 meters. Like that, and then in the other direction you'll see it's 25.7 meters. Okay, let's get started now with the different questions to look at. We're going to be starting with question 1 now, which is looking at determining the peak wind pressure for the design of the building. So these will be the pressures that we use to calculate our loads, but they can be applied anywhere to the structure. They're totally independent of geometry, except for at what height we require them. So let's get going with question 1. First thing we need is the fundamental wind speed. Here you'll see a map of South Africa. This is the wind map. This is figure 1 from the code, and we're looking at the eThekwini municipality, or Durban. And so here you can see the basic wind speed we require is 36 meters per second. So this is from figure 1. Now we also need to have a look at what is our design life, and this is a typical industrial warehouse. So we would generally use a 50-year design life, unless we had a really good reason to go more if it had to have post-disaster function, or less if it was a temporary structure. So there you can see our probability is not adjusted, or the wind speed is not adjusted with our probability, so it's CProb of 1. Now we need the terrain category to get the roughness, and which significantly influences the wind speed. Here you'll see the values and the map, and the different roughness configurations, the roughness categories. Now we must have visited site or gone to check out what's happening there and used some aerial images, and from site visits we've determined that it's between B and C, and so from that we can then pick values from the table here, and we're going to interpolate between these, and so this is using table 1 and table 2 together. We're going to get the following values. Once we have that information, now we need the reference height of our structure. So this will be at what height do we calculate the wind pressure for designing it. And we need two different heights. Firstly, since the height of our building is less than the breadth, we're going to use one zone. We don't need to have multiple zones up the side, as you can see shown here. For higher or taller, thinner structures, you can apply multiple pressures all along the side, but here we're just going to use a single load, single pressure along the side, which makes our lives a lot easier. So that's from section 8321. And then at apex, so this is at the top, this is about 5.5 meters above the ground, and this is for all zones. For all zones, we're going to use this, except D. And now eaves, this was about 4 meters. And we're going to use this for zone D calculations, because zone D is the windward wall, and the code says that for the windward wall, that is where we then have the different zones, and also we use the height at the eaves, not the maximum height, and we only adjust it for this zone, but then we'll apply it through. And now, and since ZE is greater than ZC, it's okay. ZC is the height at which no reduction can happen below this level. That's to do with the fact that you have accelerations due to the roughness of local buildings and trees and other obstructions. Below ZC, you can't adjust the wind speed anymore. So it's a fixed wind pressure up until ZC, and thereafter it drops, well, thereafter it increases with height. Now we've got the reference height, we need the topography factor. In this course, we're not going to be doing all the advanced topography calculations, so we're just going to assume now the local topography, the local slope, is not having an influence, so we're going to take that as 1. Just be careful in consulting, make sure that that assumption is true, that you don't have slopes around the site influencing the wind speed. Once we have that, then we can look at our roughness or height coefficients. Now this adjusts the wind speed based upon the roughness. So this fact is calculated as follows. Now the Z value here, this has been determined above. This is the height at the apex or at the eaves. So we're going to use those values and then calculate a roughness at those different heights. So I'm going to need this twice because I'm going to be working out two different wind speeds. Plugging the values I've selected in above, I get to either 0.806 or at 5.5 meters above the ground, I get to a slightly higher value, which will give us slightly higher wind speeds and slightly higher pressures. Once we have this details, now we can work out what our peak wind speed is. Here's the calculation. So at some height Z above the ground, we have our roughness influencing the wind speed, we have our topography factor, and then we also have our base, the peak wind speed. peak wind speed. Now our peak wind speed is just 1 times the value calculated earlier, so that gives us just the 36 meters per second. And now, plugging those values in, we can get our peak wind speeds at either 4 meters, and then this will be 29 meters per second, or we can have our value at 5.5 meters, giving us 30.5 meters per second. So now we can take this through and get a peak wind pressure, because we need to convert a speed into a pressure, and then that pressure is ultimately what's going to govern the design of our building. So here we have peak wind pressure. So here you can see the equation for the peak pressure, and it's half times the density, so the density of the air influences our results. As you get higher above sea level, the density drops. Here you can see the table showing the different densities, and we will just linearly interpolate between the different values to get the density at 350 meters above sea level, and then we have the peak wind speed, which we've covered, calculated above. So at 350 meters above mean sea level, I'm just going to use our values that I've picked from the table. Now, for this value, you don't need to adjust it for the height of the building. So if the building's 5 or 10 or 15 meters high, you don't really need to worry about that too much, unless it's a very high building that you're talking about. But then once again, very high buildings, this code doesn't apply to. Once we've got all of that, we can now get our final pressures. So here we can have the final pressures that we've calculated, either 0.482 kPa or 0.533. And when you get an answer, just sort of have a bit of a sanity check to see that what you're getting makes sense. Now, 0.533 is about 50 kilograms a square meter. So it's one sort of lighter person standing per square meter, sort of fairly light adult, standing per square meter on every square meter all at once, and this would be on every square meter of walls, and then that load applied laterally to the side walls as well. Now in the next steps we're going to use this then to calculate the pressures on the building. We're going to continue now with question 2 of our work class example, which says determine the external pressure coefficients for the roof and walls when the wind blows from grid line A to C, that's part A, and then B, grid line 1 to 6, and then show these on a diagram. I've already put together a diagram here with a plan view of the warehouse we're looking at, but then I've already marked up all the different zones we're going to get to, but we're going to see how we get there. But first we're going to have a look at when the wind blows from A to C. So that is now part A. And that is when then theta equals 0 degrees according to the diagrams of the wind direction relative to where the roof pitch is, or the apex is. And so that is then wind blowing from left to right, as the diagram shows. And it doesn't matter if theta is 0 or 180, if it blows from left to right or right to left. Because the building is symmetrical, it doesn't matter. If this was a monopitch roof with a single slope, then it theta equals 0 or 180 degrees has a big influence on your results. And then B, we're going to have a look at then from grid line 1 to 6. And then this is for theta equals 90 degrees. So that is the wind coming from the bottom and hitting the gable wall. So that's the wind coming from there. And we need to now get to where are these zones, A, B, C, D, E, F, G, H, I, J, and then how big are they and how are they orientated. So we're going to be going through all of that now. So firstly, let's just recap of what I was saying now. So for wind from grid line A to C, direction is theta equals 0 degrees. And then also what we need is the dimensions that we're going to use for the different the calculations. Now the important ones are B, which we find is 25.7, D equals 15.7 meters. And then, so this is to outside of sheeting. I've used the outside dimensions, although normally it's not going to make a big difference if you make it to the middle of the grid lines, but I've made it to the outside of sheeting. And then also the height of the building, 5.5 meters, as we looked at in the previous example. Now, on the diagrams we're going to be using, there's a parameter called E, which is just a function. It's the minimum of the breadth, or 2 times the height. So this is the minimum of either 25.7 or 2 times 5.5 meters, and then this gives us 11 meters. Therefore, E is less than D, so use figure 8b. Here you can see in the code a picture of the different diagrams and layouts, where you've got 3 different diagrams showing different classifications, and you've got your zones A, B, and C on the sides, and then D on the windward wall, and E on the leeward wall. A, B, and C, if it's a short building relative to where the wind is applied. So let me go back to the dimension, to my diagram. So the wind is coming from the left hand side here. If this dimension D here is relatively short, you might only have zone A. If it is as the building gets progressively longer and longer, which is a function of the height, then what happens is you might have A and B, or A, B, and C. In this case, you can see we're using figure 8b because of the dimensions we have. Now, continuing on, size of zones. Because you'll see those A, B, and C zones have specific dimensions. I'm just going to put in the different calcs here that these are the dimensions, the widths of these zones, and these are for the pressure coefficients on the sides of the building. So that will give you the various dimensions you see here: E over 4, E over 5, 4E over 5, etc., etc. So relative to the diagram we looked at earlier with all the different pressure coefficients for both the walls and the roof pressures, then you end up with those dimensions calculated now. And then we can move onwards. So now we need our side pressures. And here we first have to have a height to depth calculation, and this then gives us an idea of where in the table we go to pull out our values. And so get a value of 0.35, and then now that means we are between 2 different values on the table. So interpolate values. Now the next important thing to see is that, well, we're going to fill in these all these values on a table just now, the CPE coefficient, so we're working with external pressure coefficients. Now, there's another requirement in the code in terms of lack of correlation between the windward and leeward wall. I'm just going to do a sketch on the side here so you know where does this come from. If you have a building, the pressures are constantly fluctuating, so if you've got the wind blowing from one side, going over the building, and then suction on the other side, there's constant fluctuations, and this can lead to, on wide flat buildings, that the maximum pressure on the one side not occurring at the exact same time as the maximum pressure on the other side. So this lack of correlation is accounted for by reducing the total resultant force from one side to another. So it's the horizontal net lateral force that is reduced by applying a factor. So what happens is that we multiply zones D and E, and this you find in the code at section 8324. And we're going to apply this factor a bit later, but we just need to remember that zones D and E, because of their lack of correlation, need to be adjusted. Now we also have to have our roof pressures, and we've got to interpolate between 5 and 15 degrees roof slope. Once we've done that for the two sections above, we can start filling in all the pressure coefficients. So I'm going to set up a table now with all the results in that you can then copy down and use. So here you can see the pressures for the side and the roof. And just to remember, we've put two diagrams together to get here. We have all our side pressures we got from one table, and then all our roof pressures from another table. And we need to put both together. Irrespective of the shape of the roof, you will always get your ABCD from one, or ABCDE, all your side pressures from the first, and then you have a look after that. Is it monopitch, duo pitch, hipped roof, whatever type of roof it is, then you get the roof CPE factors from the separate table. And now, just to remind you of what we've discussed previously, is we are working with CPE 10. In general, what we are looking at is bigger than 10 square meters. Purlins, roofs, trusses, columns, most of them are carrying more than 10 square meters of loaded area, therefore it is 10 square meters, CPE 10 we are using. If we were designing something very small, 6 square meters of tributary area, 1 square meter of tributary area, we would use a CPE 1 or a CPE 6. And then also just to remind of other things, with our roof, because we have fluctuations, so just to come back to my diagram, because we have these vortices being created, these sort of oscillations, that they can cause either upward pressure or downward pressure on the roof. Normally your upward suction is worse, and you'll see that by the magnitude, but you could actually get both directions caused by external values. Actually, let me, just to prevent confusion, I'm going to put those on the outside. So either you could have upward or downward, and remember this is the wind on the outside acting on the structure, and so either you can have an upward value and downward value. So the blue upward, and then also remember the negative value means away from a surface, so negative will be upward and then blue will be downward onto the sheeting. Okay, now that we've got all those values, we can continue on with the CPE values for the wind blowing in the other direction. So that is then when the wind blows, as shown here, from the bottom to top. So the building orientation stays the same, but what we're doing is we're shifting the wind pattern. So now the wind is hitting this gable face, so the gable face is that face there, it's with the roof on it, and well, the roof profile on it, and the wind now, where it strikes the building, where it first intersects the building, that is our zone D. So we have our zone D down the bottom here, and then our leeward face up the top, our zone E, and then our A, B, C down the length of the building. And we have to recalculate the values for the dimensions, and then once we've done that, we're also just going to fill in our A, B, C, D, etc., external pressure coefficients down the side of the building. So here we go, we've worked out the E value based upon shifting B and D around to adjust for the direction the wind strikes the building, or the direction that it is following through. Now we have to work out pressure coefficients on sides. See, now that we know our h over d is less than 0.25, we know which line of the code to take our CPE values from, and then now we just need to see, do we need to multiply our windward and leeward walls by 0.85 for lack of correlation? So yes, we do need to multiply our zones D and E by 0.5 since h over d is less than 1. And now we need to also see which line of the code do we take our roof pressures from. And then once again, we need to interpolate between 5 and 15 degrees on our roof slope. And then here you can see an excerpt from the code where the CPE values from the external pressure coefficients. And then these I'm going to go fill in the table above. So here you can see the pressure coefficients for the side for theta equals 90 degrees taken from the two tables in the code. And then just a reminder, or just a clarification in case this thought comes up, when it comes to the 0.85 factor, that is, remember, for lack of correlation between windward and leeward wall. If, for instance, I was designing a girt on the windward wall or on the leeward wall, and I was only looking at one side, I wouldn't use that 0.85 factor because I'm not looking at both sides together. It's only when I'm looking at a model where both sides are acting and both sides are considered at the same time will I use that 0.85 factor. If I'm just looking at one side on its own, I will use the unmultiplied factor, or just 0.85 won't be there. So just a clarification in terms of that. Okay, but that takes us through then the CPE, the external pressure coefficients. So those account for the shape of the building and how the shape of the building influences pressures. And so those are then graphed as follows. And then just to remind you of where you have these edge zones here, especially corners where the roof strikes, and then just over the apex of the roof, there you'll see, for instance, zone J, the CPE is much higher than zone I, or zone G and F are much higher than H, and once again that is to do with these vortices at the corners where you have much higher suction pressures being created because of the turbulence. So we account for those locally by having these thinner zones of high pressure. We're going to continue on with question 3 now, which says, determine the internal pressure coefficient when the wind blows from grid line A to C when both doors are open, and B when doors are closed. So we've got two parts of this, but the wind blowing in the same direction. So I'm just going to quickly go back to our diagram. So we've got the case, we're now back at wind blowing from grid line A to C, but we've been told that there are some doors on this building. We've got a roller shutter door on this side, which was explained at the beginning, and then we also have a small pedestrian door on the end. And then also we have some leakages. There's about 30mm gap between the sheeting and the side walls, and I mean that gap in reality could be all over the show and depends on the quality of installation, depends on flashing details, depends on all sorts of things. But now we need to work out the internal pressure coefficient, so that how pressurized is this inside. So let's go back down. And so we're going to start running through these calcs to find out how to apply this. First thing we need to know according to the code is areas of openings and which is a dominant wall. So I'm going to run through some calcs and then we're going to discuss them. So looking at the calcs here, what we first done is took the background permeability, which was 30mm, and then multiplied that by the perimeter of the building, so 2 times length times breadth, and we get a rough area of leakages that are occurring. Then we've also got our roller shutter door, which is just, we've got given dimensions, and we've got our single pedestrian door, which is about 2 square meters. Now, that tells us that the area of the roller shutter door is greater than twice the area of the everything else combined. That means the roller shutter door face is dominant, and then further than that, the area of the roller shutter door is greater than 3 times the area of the other leakages or other openings combined. That means our CPI, our internal pressure coefficient, is 0.9 CPE. And then, just as a note, we need to make sure that we use the CPE where the openings are. And we're just going to go back and discuss that now, and just the physics of what's happening. Because we've got our wind blowing from grid line A to C. I'm just going to find my diagram. And now the wind is coming across from left to right. When the wind hits the building, we've got now positive pressure all along face D, and then at the same time we've got negative pressure along grid line E. But what happens is if we have a look at our diagram through the section, just to try picture this, here is our section through the structure. We have our wind onto it, and we've got suction pressure. The fact that we have a big roller shutter door here means that when it is open, when there is no door blocking the wind, this air on this side will suck the air out. So what will happen, it'll create a net suction inside the whole building. So the CPI is always a factor of where are the leakages. And this example is relatively easy because the openings, the dominant face, just has one pressure coefficient, zone E. So we just have a look at zone E here. And so this would be CPE E. So this is a function of the pressure in zone E. That is then what is of consideration. If, for instance, this door was in a different zone, just as an example, let me go back. Let's say our dominant face was up the top here, and it fell across zones A and B. All we would do is find out how much falls within A, how much falls within B, and then we can take a weighted average of the 2 or the 3 if it falls across 3 zones. But once again, we look at CPI is a function of what is happening outside where the big openings are. If you have multiple openings, then you've got a different way to approach it, which we'll get to in the next question. But when you've got, firstly, we found that there's a dominant wall, and then that wall affects our pressure internally, and the fact that it's very dominant, it's 3 times greater than all the other openings combined. It means this internal pressure is 0.9 times the external pressure, because at that opening it's sucking the air out, creating that negative pressure. So if we come back and now go down to question 3, we can now finish this off. Therefore, so as I mentioned, so your CPI, your internal pressure, is now a function of the external pressure at zone E, and there was a suction, so we are creating a suction within the building. So it is pulling away from all the surfaces, sucking it inwards. We're now going to go on with part B of the question, which states that determine the internal pressure coefficient when the wind blows from grid line A to C when B, the doors are closed. Now, in a real building, if the doors are closed, but you've got a big warehouse, you can have all sorts of leakages. You've got louvers and vents and smoke vents and openings that they add, or things that are not properly sealed or flashed, or all sorts of things. So it's very difficult to accurately quantify it. If you've got a very formal building with distinct openings, then you can quantify it reasonably accurately. But for the sake of the course, we're not going to go through into all the detailed calculations when you've got lots of openings in different zones. So we're going to just use a simplified guideline whenever you have different openings and not really a dominant wall. So, as I was saying, if you've got all doors are closed, leakages are difficult to accurately quantify. So from clause 8.3.9.6 in the code, we use the worst, which is described as more onerous, so which will give you the worst answer of plus 0.2 and minus 0.3. Now either could govern. It depends on what load case is worse. Okay, we're going on to question 4 now, which says determine the line loads in kilonewtons per meter to be applied to the worst case internal bay portal frame when the wind blows from grid line A to C and the doors are closed. Only calculate the worst case uplift forces. So I'm going to zoom out and just go back to our layout and then to our CP factors that we have calculated. So here is our layout. And we've got to pick a portal frame to analyze somewhere within the structure. And then normally the portal frame that we'll need will be somewhere in the middle of the building, because it's got then a tributary area from both sides. It's getting loads from both sides of it. It is possible once in a while that the end portal frame governs, so right down on the gable face, but normally it's got half the amount of load on it, so the pressures will have to be more than twice the rest of the structure for it to govern. And in this case we do find out that one of the internal portal frames along this line governs behavior. Sometimes with an internal bay you may find it just overlaps with one of these corner pressure zones, so then you have to adjust zone G to be a weighted average between zones G and F, but then just have a look at each case where's your portal frame that you're analyzing. So now we're going to analyze a portal frame running through, and we're going to then apply loads. So just to stay there again, we're going to apply a tributary width. So the bays are 5 meters apart. That means there's about 5 meters of load sitting on your structure, because the portal frame sits in the middle, but it receives 2.5 meters of load from one side and 2.5 meters of load from the other side, and then the next portal frame sitting there will receive something similar. Now that means we need zones D, G, H, J, I, and E in our calculation. So those are the ones we're going to do now. We're going to work out UDLs on this portal frame from those. If we were doing throughout the building, we could also get for other areas, but we're only going to do those specific zones because they're going to act on our structure now. And also it says we have to look at which load case gives us the worst case uplift. So we want as much load pushing up. So we want maximum suction from the outside and maximum internal pressure from the inside. And then we're going to be applying these CPE values. Just to make a note, I realized there was a mistake with J. Please correct it to be as shown. It should be minus 0.8 and plus 0.1. And when you write this down, you can often pick this up, is that J is just over the apex, so you expect higher pressures just over the apex where the turbulence is. So these are the corrected values then for J, so please just update your notes with those. And now we're going to come back and start running through question 4 with all of that. So I'm just going to write out what we've discussed now. So there's our discussion, loads on frames at 5 meter spacing, and this is assuming simply supported purlin, so it's exactly half the loads goes each way. Our UDL, uniformly distributed load, is our tributary width times our pressure times by CPI or CPE. In the diagram below, we're going to show two pressures, one from the outside, one's from the inside. However, there's absolutely nothing wrong with otherwise applying a net force, omega W, a resultant, or net, which is a tributary width times CP at the height, and the CPR, a resultant CP factor, which is CPE minus CPI. You will then get the same answer whether you add the total UDL to the total internal CPI value, or you work out a resultant. Either way is fine, but it's just good to have that understanding of the application. I'm going to apply them separately just so you can see the influence of your 0.85 factors and other things. And as we said, for worst case uplift, use negative CPE values, so you want as much suction up and then enough the maximum positive value from the inside. And then as mentioned, for theta is 0, all internal bays have the same load. Now we're going to then run through and calculate the UDL on all the zones below. So here you'll see all the zones with the zone, the pressure to be applied, CP value, either CPI or CPE, the uniformly distributed load, and then the resultant pressure coefficient. A couple of things just to note. Firstly, in terms of pressures, remember on our windward face, we applied the pressure at the eaves. Everywhere else we have applied the pressure at the apex. And then also with the CP values, I've applied it as 0.85 there, and that gives us the pressures to apply depending on whether we are using the total resultant, where we will use 0.85 and the 0.71, or if we are just looking at one side, we will use the 0.71. That's why earlier when I was calculating the CPI value, I just used the 0.33 value, simply because the 0.85 is for lack of correlation. I used the full value conservatively at the pressure, assuming that it was at the maximum. It was causing the maximum internal pressure coefficient. I did not apply the 0.85 to the CPI. And then we run through and then we get all the values that we can apply through. Now, once we've got all of these values, we can then go and apply them to the diagrams that I'm going to show below. So here we have some portal frames, and here is the external pressure coefficients, and we're going to we've put in all the different pressures on here showing how it changes. And just remember now, if we are analyzing the whole thing, this should be multiplied by 0.85, and that should be multiplied by 0.85, and then once again you've got your high pressures at the corners, and then your pressure on zone D, suction on zone E. And here we have, with the internal pressure coefficient, everything's pushing out because we took the plus 0.2 CPI value, and then applied it throughout. Now, once you've got these two diagrams, you can then now apply that to your structure. And in your finite element software, in your Procon, your Abacus, or whatever you're using, Strap or Strand, or the various other ones that are available, you would apply either the external pressures and then a separate load case, the internal pressures, or you could just combine them and apply a single combined pressure together. It depends on your analysis and how many cases you're doing, whatever's easiest. Either would get you to the same answer. It just depends on how many load cases and combinations it would what would be the easiest for you. And then normally the software will just convert those distributed loads to point loads at each node of your model. Otherwise you could do that yourself, just multiplying the UDLs by the distance between each node you are working with. Okay, so that takes us through and then how to get from a pressure and wind speeds right at the beginning in question 1 right through to now distributed loads that we actually can physically apply to our structure, and then run the analysis to get to an answer. We've only considered one specific case here with maximum pressure uplift, but you could have multiple cases with different CPI values, different CPE values, because also you can have cases where it goes up on one side and down on the other, etc. But as I mentioned earlier, this can give you 32, 64 and many more different cases, but normally a good structural engineer can look at this and break it down into a small number of wind cases that will govern the design, and then work with those in the rest of the combinations. But then in the next video we're going to go on to load combinations and applying these wind loads we've calculated in collaboration with other loads, dead loads, live loads, and how do we combine them in a global structural analysis. Thank you.